Hi everyone, I'm Beth.
And I'm Jack.
And in today's Lunchtime Lab, we're going to teach you a bit about oceanography, which is the study of oceans and how they work.
In this Lunchtime Lab, we're going to walk you through a few experiments that we've performed, which will help you to understand some of the things that we, as oceanographers, have got to understand and think about when we look at the oceans. And some of them you'll be able to do along with us at home. At the end, we're going to take you down to the tank room and there'll be some robots there, and we can show you how they work and how we use them to help us study the oceans. In this experiment, we're going to look at something called density. Density is a scientific word which explains how much material there is in a certain space. To look at this idea, I've got a wooden block and a metal block in front of me. Both of them have a mass of 100 grams, and because they have the same mass, that means that in my hands they feel pretty much the same. However, of course, the wooden block is a lot bigger than the metal block. That is because in the metal block, all of the particles and atoms are packed into a much smaller space. But you could say that there's pretty much the same number of particles, but just in a smaller space. So that means that this metal block is more dense than the wooden block. Why is density an important thing for us as oceanographers? Why does it matter? It's because in the water in the oceans, the density of objects controls where they are, whether or not they're at the top or at the bottom. And to explain this, I'm going to put these objects in the water. The metal block sinks to the bottom of the water very, very easily, whereas the wooden block sits on the top, even if I try to push it down. That's because in water, if an object is very dense, then it will sink down to the bottom. But if, like the wooden block, an object is not very dense, it will float at the top. And in water, different things can make water have different densities. So if you get water which is very dense and water which is not very dense, then the water which is very dense will sit at the bottom, and the water which is less dense will sit at the top.
So there are a few things that we have to think about when we study the ocean, and these are temperature and salinity, or how salty the sea is. So we think about these because these have an influence on density. First off, our temperature. If something's really cold, it's going to be more dense and sit at the bottom than something which is hot and going to be less dense and float at the top. So if we had cold water, it would be underneath hot water. Whereas if we look at salinity, or how salty or fresh something is, so fresh means water that's not got very much salt in it, and salty is water that's got lots of salt in it. So salty water has all the salt particles mixed in with the water, and that makes it more dense, so it will be at the bottom, whereas fresh water will float at the top because it's less dense. So we have to think about all these things when we're studying the ocean. And what we're going to do now is we're going to take two very cold ice cubes, and we're going to put one in our tank of salty water here and one in our tank of fresh water. And we're going to have a look at what happens and use that to show you a little bit more about density. So what do you think might happen before we put them in? I'm back with two ice cubes, and we're going to pop these in our tank of salty water and our tank of fresh water to see what happens. So these ice cubes have been made with purple food dye so that you can see the water spread out throughout the tanks as they melt. Now ice is less dense than water, so when we put these in the tanks, they're going to float on top of the water, but the water that melts out of the ice cubes might do something different. What do you think might happen when I put these in? Let's find out. So we can see now our ice cubes are in our tanks of water, and if we look at our fresh tank first, our ice cube is starting to melt, and we can see all this purple water that's really cold and fresh from our ice cubes sinking down to the bottom of our tank. And that's because this cold water is more dense than the room temperature water that's in that tank already. But if we look at our salty tank, things look a little bit different, and why might that be? So our ice cube is still melting and giving out really cold water, but this time it seems to be floating at the top. And that's all to do with the salinity of our tank. So remember, this tank is full of really salty water, and what's happening is we're putting fresh water into that, So our fresh water is floating at the top because it's less dense. So that's the fresh water from our ice cube melting. Even though it's cold, it's still floating on top of the tank.
Cool. So to recap, in this experiment we've been looking at density. And if we remember, there are two things that affect the density of water. That is the temperature and the salinity. We saw that the temperature affected the water in the freshwater tank because the cold water coming from the ice cube sunk to the bottom. So we showed that cold water sinks. In the salty tank, we showed that salty water sinks because the salt water in the main tank stayed below the fresh water with no salt that came out of the ice cube.
So if you like this experiment, you can try it at home by getting yourself some table salt, a container, some tap water, and some food dye. Now you might need a parent or guardian's help to do this one. And you're going to freeze some ice cubes with some food dye mixed in. Now use gloves so you don't stain your fingers. And then mix yourself up a salty tank and a fresh tank. You can make your salty tank by using 35 grams of table salt in a litre of water. And take your ice cubes once they're frozen and have a look and see what happens when you put them in the water. Do they sink or do they float? So now we're going to take a tank of salty water and a tank of fresh water, some pencils and some plasticine, and we're going to look a bit more about density and try and teach you about buoyancy. So if we take a pencil and put it in a tank of fresh water, what do you think might happen? So it floats up to the top, and this is because our pencil is less dense than our fresh water. Whereas if we take some plasticine, what might happen here? Pop it in the water, it's more dense than the water, so it sinks to the bottom.
So now, what might happen if we take another pencil and a blob of plasticine and put the two of them together to make one object? I'm going to start with just a little bit of plasticine and put it on the end of the pencil, like that. Okay, so if I put this now in the tank of fresh water, do we think it will float because the pencil's less dense in the water, or sink because the plasticine's more dense in the water? It floats to the top, and that's because there's not very much plasticine, so the density of the overall object is less dense than the fresh water. But what happens now if we put even more plasticine onto the object? Okay, that's quite a lot of plasticine that we've got on the object now. So what happens if we put this back in the fresh water? That sinks to the bottom, which means that now, because of the extra plasticine, the overall object is more dense than the fresh water.
So earlier, we took a pencil and put just the right amount of plasticine on it so that it'll have the same density as our fresh water. So what do you think might happen if we put this in the water? Let's see. So what's happened is our pencil has hovered in the water just where we put it, and that is because it has the same density as the water. And this is something called neutral buoyancy.
So what happens now if we take this pencil out of the freshwater tank, if I can actually grab it, and put it in the saltwater tank, which we know is more dense than the freshwater tank? Will it float, sink, or be neutrally buoyant in this tank? Let's take a look. It floats in the salty water tank, which means that this object, which is the same density as the freshwater, which is why it was neutrally buoyant in this tank, is less dense than the salty water.
So earlier we prepared a pencil with some plasticine on it, just the right amount of plasticine so that it's neutrally buoyant in our salty tank here. So if we pop this in the water, again, it's going to hover just where we left it, and that is because it has the same density as the salt water.
So what do you think will happen now if we put this pencil and plasticine back into the freshwater tank? Will it sink, float, or be neutrally buoyant? Remembering that the fresh water is less dense than the salty water, and it was neutrally buoyant in the salty water. It sinks to the bottom, which again is what we expected, because the fresh water, it's easier for things to sink in it because it's less dense. So this object is more dense than the fresh water.
So just to recap, we've shown you that our salty water is more dense than our fresh water, and what neutral buoyancy is, which is where our pencil and our plasticine had the same density as the water it was in. So you can try this experiment at home. If you get a clear mixing bowl, you measure out 35 grams of salt and put it in a litre of water, mix it all together, find yourself a pencil and some plasticine, or if you don't have any, some blue tack will work too, and see if you can make your pencil float, sink and be neutrally buoyant in your bowl of salty water.
In this experiment, we're going to be salt tasting, which is something that you guys at home can join in with us for. In front of me, I've got 4 different containers full of different amounts of table salt, and soon I'm going to add some water into all of them and stir them up so that they all look the same. A fun fact that you might not know is that different seas and oceans around the world are not all exactly as salty as each other. Some of them are more salty and some of them are more fresh. The table on screen now is showing how to make these 4 different solutions at home with your own table salt, water and containers. I'm going to add water to these 4 containers, and once I've done that, I'm going to bring Beth here and she's going to try and taste the 4 different samples and see if she can work out which one represents which sea and which ocean from around the world. Welcome, Beth. In front of us, we've got 4 different containers full of solutions of salty water, and all of them have different amounts of salt in. They represent different seas and oceans from around the world. The seas and oceans that they represent are melted Antarctic sea ice, the Baltic Sea, the Mediterranean Sea, and the Dead Sea, but they're not necessarily in that order. So your job is to try and take a small taste from each of them and work out by how salty they are, which one's which. If you're doing this experiment with us at home, please be careful when you're tasting the different solutions of water, because the salty ones will taste rather nasty and it might make you a little bit ill. So please only taste a little bit and don't swallow any. So can you talk us through which ones you would expect to be the most and the least salty and why?
Okay, so I think the melted sea ice from Antarctica is going to be the least salty. And that's because sea ice doesn't really have much salt in it from where the water in the sea is frozen to make the ice. And then I think the one from the Dead Sea is probably going to be the most salty. And that's because the Jordan River flows into the Dead Sea, but there's no rivers that flow out of the Dead Sea. So the water evaporates that's in the Dead Sea and goes up into the air, and that leaves all the salt behind and makes it really, really salty. And then the Mediterranean and the Baltic, I'm not sure which way around they're going to be, so I'll have to taste them and find out.
That's interesting, thank you. I'll let you taste them now and you can see.
Okay.
I'll switch sides with you. How did that one taste?
It's a little bit salty, but not too bad.
Okay.
Ooh, that one tastes a bit more salty.
Oh. Okay, number 3.
That one tastes almost like regular tap water. That tastes quite fresh.
Interesting, okay. Number 4.
Oh, that's very salty.
Oh, interesting.
So I think number 4 is going to be the Dead Sea, because that's the saltiest by quite a far. I think number 3 is going to be the sea ice, because that's the freshest. And then the Mediterranean and Baltic, I think the saltier one, which was number 2, is going to be the Mediterranean, which makes number 1 the Baltic. Was that right?
Well done, that was 4 out of 4. That was a very good effort indeed. So perhaps we should give a quick explanation of why the Mediterranean is more salty than the Baltic, because they're pretty close, but there's a little bit of a difference. There's a little bit more rain over the Baltic Sea, which means, and of course, rain is fresh water. So if you get rain over a sea, it makes it less salty, which is why the Baltic is more fresh than the Mediterranean. Wonderful, you did a very good job there.
So we hope you were able to work these out alongside us at home, but if not, just to recap, number 1
was the Baltic Sea.
Number 2
is the Mediterranean Sea.
Number 3
is the melted Antarctic sea ice.
And number 4
is the Dead Sea.
Thanks for joining in. So next we're going to show you a little bit more about density, and we're going to teach you about pressure. Now pressure is the force acting in an area. So if I take my fingers and push against the bottle here, you've got the force of me pressing on the bottle, and the area that's happening is where my fingers are touching the bottle. And what we're going to do is we're going to use this idea of pressure, and we're going to show you how it works by using these little divers that we have in our bottles here. So in water, you can't really squash water very far because all of the bits that make up the water, the molecules and the atoms, are already really tightly packed together. Whereas in air, which is a gas, all of the molecules and atoms that make it up are spread out all over the place, and they're all whizzing around really quickly. And so we can squash them all together and make it a lot smaller.
Cool. So as Beth says, if you put pressure on the outside of the bottle, then that pressure increases the pressure inside the bottle as well. So what happens if I start to squeeze the bottle, I'm increasing the pressure on the outside, and that pressure means that everything on the inside is trying to get smaller. But as Beth says, you can't really make water smaller, however you can make air smaller, and these little divers on the inside of the bottle, there's air inside them. So when we squeeze the bottle, the air inside the diver will start to compress inwards, and as it does that, the little hole in the back of the diver will start to suck the water from the bottle into it to fill the gap where the air is getting smaller. And what that means is that as the water is going into the diver is going to get denser because there's more material inside it. And as it gets denser, that means that if I squeeze it hard enough, it will get denser than the water in the bottle, which means that it sinks. And now, if I start to release my pressure, so if I start to lighten my fingers, then the air inside the diver will start to expand outwards again, and that means that it's become less dense than the surrounding water once again. For our final segment, we're here in the tank room at the University of East Anglia, and we're going to look at one of the robots that we use to learn about the oceans, which is here in the tank next to us. We're also going to look at this glider here, which is clear, which means that we can look closely at the inside of it to see how what's happening on the inside of this one, which is exactly the same as the inside of that one, affects the way that it moves.
So if we think back to our pencil buoyancy experiment that we did earlier, we managed to make our pencil and our plasticine together neutrally buoyant, so it's sat in the middle of our tank. That's exactly what we've done with our Seaglider here, ready to do our experiments.
So how does this glider move, you might wonder? It doesn't have an engine on the inside of it, like a car or like a ship. And that's because we want gliders like this to be able to stay in the oceans for lots of months at a time. And engines have to be refueled quite frequently. So instead, we've got to be very clever about the ways that we make it move. And we're going to show you now how we do that.
We're going to start by showing you how we get our Seaglider to go down through the water. Once the Seaglider is in the ocean, we want it to sink down so we can study what's happening deep down, all the way to 1,000 metres. If you think back to our bottle diver experiment from earlier, we made the diver sink by filling the diver with water as the air bubble was squashed when we squeezed our bottle. What we do with our Seaglider is very similar. In the back of the Seaglider, we have a bladder, which is a bit like a balloon containing oil. When we put the Seaglider in the water, this section of the Seaglider fills up with the water from around it. If we suck some of the oil out of the bladder and further into the Seaglider, then more water goes into this back section to fill the space where our bladder was. This makes the glider more dense overall, so it sinks.
That's great. So now we know how to get the glider to sink deep into the ocean below the surface. But right now, it's only going straight downwards. So is there any way we can get the Seaglider to travel forwards through the ocean too, so that it can explore more of it? Yes, there is. We have to make the glider point its nose a little bit downwards, and then the way the ocean water pushes on the Seaglider wings as it's sinking will push it forwards as well as going downwards. To make the nose of the glider point downwards, we have to move things around inside the Seaglider so that the front becomes more heavy than the back. So we use the glider battery, this big thing in the middle, which has a metal weight attached to it as well to make it even heavier, and we move that forwards towards the nose of the glider. Let's see what happens when we send this command to the Seaglider. So we can see that the nose of the Seaglider has just tilted down as the battery has gone forwards towards the nose. If you're wondering why the Seaglider isn't travelling forwards now that we've got it tilted forwards, it's because it's got to be sinking at the same time as having its nose pointing forwards.
Now we've seen how the glider can get down deep into the ocean, but we need it to get back to the surface. Think back to our bottle diver experiment again. The diver floated back up when we stopped squeezing the bottle and let the extra water back out of the diver as the air expanded. Again, we do something very similar with our Seaglider. If we make the bladder fill up with oil from further inside the Seaglider, this makes the bladder take up more space, which forces some of that water out in the back section, making the Seaglider less dense and help it float back to the surface through the surrounding seawater.
So now we have a glider that can move up, down and forwards. But what happens if the Seaglider isn't going in the direction we want it to go? What happens if we want to turn it? Can we do that? We can. Again, we use the battery from before, and instead of moving it forwards and backwards, we twist it, and that means that we're changing the side of the glider which is heavier. The heavier side of the glider will then sink downwards and it will cause the glider to roll. So let's see what happens when we rotate the battery. And to help the Seaglider keep moving forwards as well as upwards when it's rising, and not just straight upwards, we can do the opposite of what we did earlier and tilt the nose upwards instead of downwards, so that the glider will be rising and be tilted upwards at the same time. We can see what happens when we send this command to the Seaglider. To do this, we have to move the battery further away from the nose.
We've shown that our glider can move up, down and forward through the water and can also change direction by rolling. So now we have a robot that can explore anywhere down to 1,000 metres in the ocean. But what do we scientists do with it? So we put sensors on our sea gliders to measure lots of different things in the ocean. This glider in the tank has sensors in 3 different places, which help us measure temperature, salinity, pressure, amount of light in the water and amount of chlorophyll in the water. We can add other sensors to our sea gliders to measure even more things, like the amount of oxygen in the water, or even listens to sounds that are in the water. When we launch our gliders into the ocean, we use measurements like these to learn more about what happens in the ocean itself. The glider group has previously studied areas of the ocean where the oxygen levels are becoming so low that animals can't survive. In other areas, we've managed to use sea gliders to go out and listen to whales. So when our gliders are out in the ocean, we can't plug a cable in like we did in the tank to give commands. So what do we do instead? We have to use satellites to talk to our sea gliders and tell them where to go. So then the sea glider does lots and lots of calculations whilst it's under the water to change its pitch, its roll and its density, just like we saw in the tank, so it can try and reach its target. The sea glider can stay in the water for months at a time before we go and pick it up with a ship. So now you know lots about sea gliders and how we study the ocean with them.
That's it from Beth and I on this Lunchtime Lab on sea gliders. We hope that you've enjoyed watching these experiments and learning about the robots that we use to study the ocean.
If you've got any questions, pop them in the comments down below. And if you'd like to learn more about the missions that we do with our sea gliders, go to the UEA Glider website with a link down below. Thanks for watching.